Cheryl will be like,
proud.
well,
It's a one
done,
choice.
Josiah.
You might need that.
I will have it every day
From
from next work.
the blah, blah, blah.
Right now, the second, can't
I
start
was
off
gonna
last
say
week.
the person from every day and be like, welcome to class.
I already brought Dr. Kager an apple this year.
No.
He laughed, because nobody said he had this old second editions of the computer systems. Back then. Yeah. He's like, "These stuff."
That's weird.
I brought that PC. I was like, we got it every day.
Yeah, the CSC network is super weird all day.
So logging in down there, I use my old password. Logging in here, I use my new password.
Yeah, I only have one of those.
Like reimage.
Oh, yeah, it has one.
Oh, yeah.
There's two networks that are.
Oh, you gave your third.
Today, when I went to get onto the engineering zone drive, you have to use your new password to get in, and then when you try and connect to the engineering capstone drive, you have to use your old password.
Very nice.
Yeah.
Okay, so last finishing up chapter 1, talking about design considerations of the stress and strain stuff that we've been talking about. So, just as a curiosity, who has logged into mastering engineering and maybe done a problem or 6? Okay, very good.
I have to talk to you
Oh, really? All right. Try to finish your food before you talk to me.
No.
All right, so so I'm assuming no issues. Everything's hunky-dory for everybody.
Yep.
Okay. Well, I mean, maybe the problems, but I mean, the process is, everything's good.
Yes.
Okay. All right, so implications for design. The key with design is, in terms of stress and strain, is just because you can doesn't mean you should. In other words, just because you find that this particular hunk of steel, we're not cutting into your social calendar at all there, are we?
No, it's in the machine shop.
Just because a particular hunk of steel could hold 1,000 pounds, doesn't necessarily mean that we should design it to hold 1,000 pounds. Okay? Because we're always going to have to include some kind of safety factor. To allow for the possibility that variables beyond our control may be present. So the book calls it a factor of safety as opposed to a safety factor, but whatever. So the factor of safety is the ratio of the force that would cause a failure to the ratio, or to the force that we're going to allow. So if I have this specimen and I'm going to apply a force on that set specimen, it might fail at 1,000 pounds. But I don't want to design it to hold 1,000 pounds because something might happen. I mean, you never know. For instance, we're walking through the building. The building has a certain amount of weight, right? This floor has to hold a certain amount of weight, right? So it has to hold a certain force. And we might design it to hold 7 people and the chairs. So we'd be good. But then what happens when one of them jumps up and down? Well, suddenly, for that instant, there's more force than just the 7 people. What?
I think when you jumped, it like,
Oh, did it on its
I
own.
got scared.
So, that instant that I land, there's more than 7 people's worth of force, right? So we have to allow for a safety factor because there's going to be variables beyond our control. Somebody's going to stuff that 11th person in the elevator designed to hold 10, right? So if we went to, another way to look at that is then the allowed force is going to be whatever the failure force is divided by that safety factor. So what's the safety factor going to be? It's going to, what's a nominal value? What's a limit for the fixed safety factor?
a limit?
A limit. Right, so what is the limit of the range of values that a safety factor might have? The largest or smallest possible safety. 1. Right. So we're always going to design something with a safety factor that's greater than 1. Right. If you have a safety factor that's equal to 1, then you're not actually including a safety factor. And if it's less than 1, you're trying to tear the building down. So safety factor is always going to be greater than 1. Typically speaking, for sort of generic structures, footbridge or a building or anything that is going to house people and and have essentially a great deal of liability associated with it, you're going to use fairly large safety factors. If you're flying an Air Force fighter, you're going to use much smaller safety factors. Not because the Air Force pilot is less valuable than other people, but because it's designed for a critical mission, they're going to try to design it on the edge, right, to get absolute maximum performance out of it. Okay, so the factor of safety depends on the application.
Is that F-A-L-L-O-W?
No,
Allow.
it's the allowed
Force of
force
allowed,
and the
okay.
failure force.
The fellow.
Yeah, the foul force
That's
and
right.
the failure.
The force of failure divided by the fallow. Okay. And in cases where the stress and the force are linearly related, we could also say the failure stress divided by the allowed stress. And again, the allowed stress is going to, or the stress is going to be the better way to characterize what we're trying to do. We don't necessarily do it in terms of force, we always calculate it in terms of stress. Because stress is a material property, force is not a material property. Force depends on geometry. Right, because a large sample is a smaller force per unit area. So, or anyway, smaller stress. So this is generally not true in cases of where there's like buckling, like if you push down on a column, the column will kind of barrel out. You know what I'm talking about? Well, when it barrels out, we end up with a non-uniform stress distribution because of that barrel. So this linear relationship is not always going to be true, but for most of the stuff we talk about in here, we're going to assume it's true. And this is the way that we're going to use the safety factor in most cases. Or if it's a shear failure, tau failure divided by tau. Wow. Okay. All right. And in general, when we're designing things, we don't design around force, or the force is fixed, right? So in other words, I'm building a bridge, I have a fixed amount of force that bridge has to support, right? I got to drop a certain number of lanes, or a certain number of cars, or whatever it is. So it's usually force that's fixed, and the thing that we design around is the geometry of the problem. Right? So I've got a rod that's got a hold of force. The force is given by the problem, and the force is given by the nature of what I'm trying to build. I can change the size of my rod to accommodate whatever force I need to. So in general, you're going to have a given load, like a P, keep going back and forth, P for, you have a given P load and a given material. So I've got to have a steel column, and it's got to hold 1,000 pounds. And I have to find the area of that column, right? The area of that rod, the cross-sectional area of that rod. So in other words, the area then is going to be the force divided by the allowed stress. And just inverting those. Which means it's going to be the force divided by the failure stress times factor of safety. So the size of the part, the cross-sectional area of the part will scale with the factor of safety. So I make it twice as safe, I got twice as much area, which kind of makes sense. Right? If I'm going to make it really safe, I use a bigger beam. So that kind of, I mean, it's pretty straightforward. We're just going to do problems primarily here, but does that make sense? Okay. All right then, and I actually want to, I'm going to try to go through these pretty quickly because I want to get back to, I'm going to go back and do one of the other problems from the last section. Second problem from the last section if we can. Okay, so are we ready to do problems?
Just a quick question, are the factors of safety in like real life normally given to you by like whoever's regulating whatever project you're working on?
So it depends
You
on
have it
the nature.
rated, don't you?
What's that?
You have it rated, don't you?
Yeah, so it depends on the nature of what job you're doing. If you're you know, working as a civil engineer building bridges, then yes. If you're in sort of doing a researchy kind of thing, then not so much.
Like software related?
Yeah, because you're designing a part, you know, in other words, you guys are, you're building the satellite, right? There's no regulated, defined factor of safety for the, the strength of your antenna boom or whatever, I mean, yeah, right? So you just have to figure that out on your own because it's your own sort of design. So it just varies depending on the nature of the problem. Okay, any other questions? All right then. So let's do number 171. We have a joint fastened together using 2 bolts. Determine the required diameter of the bolts if the failure shear stress is 350 megapascal. So we have tau failure is 350 megapascal. And we use a factor of safety of 2.5. So we have to find the diameter of the bolts. So what shall we do? Where shall we begin?
We need a free body.
We need a free body diagram. Right? That's generally what we're going to start with every problem. So, a free body diagram of what?
I would say bolts, right?
Okay. Free body diagram of a bolt. So I've got a bolt. I'm just gonna, this is not really a free body diagram, but because I don't have a good drawing of the rest of the thing, let me do it this way. Okay, that wasn't quite so perfect, but anyway. Okay, so that's what we've got. And that's kind of a zoomed in picture of the bolt. So if we want to just do the free body diagram of the bolt itself, we have the bolt, and then where do you want to, what kind of forces do you want to draw? What do we got?
How do we draw the free body? Are we drawing it for 2 bolts or just 1 bolt?
He said for 1 bolt. We're drawing a free body diagram for 1 bolt.
Because won't both bolts split force equally between them, since the forces are symmetrical?
Right, so we can take that into account when we
Okay, so we just
put our forces on here. Okay, so what do we have?
we can sum forces. You could go.
So we don't have any forces to sum yet. We gotta draw the force, right? Free body
Right,
diagram,
right.
we gotta draw the forces.
Right, so we can put the forces in. So
Where-
80 divided by 2 going to the right would be 40 kilonewtons.
And where would that be?
Right in the center of the bolt.
Right in the center of the bolt. So we have 40 kilonewtons there. What else?
Does it tell us the thickness of the plates?
It does not, but the plates are in immediate contact.
So can we just say like 1/3? Or like half between the center and the top, is where the person has and half between the bottom, so then it's fine?
So you said you want to go 1/3.
Or not? No. I took back the 1/3.
Well, I'm gonna keep it up there.
Okay.
I like the 1/3.
Well then, in the middle of the top 1/3, the bottom 1/3.
Like that?
20 page.
Okay?
So it does technically be a distributive force, but since they're equal, we can just go ahead and.
Right, so they're technically a distributed force. Right. So you actually have this, this, and this. And we don't have dimensions on there, so it's gonna be hard to label them as such, but,
So we're just approximate.
so what's that?
We're just gonna approximate since we don't know numbers.
Well, we don't need to approximate anything.
No, they've already given us the numbers.
So we have these numbers, we don't know kilonewtons per inch or anything like
Yeah.
that for these distributed things. We
That's
just
fine.
know that the total is 20 kilonewtons.
Okay, gotcha.
Okay, so I'm to approximate. Okay, so there's our free body diagram. Now what do we do?
Okay, so.
What kind of failure are we going to talk about here?
Sheet.
Shear failure. All right, so we're going to want to do an analysis of shear loading on this pin, on this bolt. You guys remember how to do shear?
Can we like pretend breaking it, right? Pretend that we're.
Or so take a cross section.
Sections, yeah, sections.
Yeah, right. So we can do a
At
section.
the third, at your dotted lines.
At the dotted lines, right?
Mhm.
So if you remember from, I'm assuming you did this in statics, do you do shear plots in statics? So
Right at the end.
if I did a shear plot of this thing, right? I have 0 shear at the end. I have an increasing value shear, right? It's the integral, you integrate the area under the distributed thing, remember? And then I have this, and then it comes back down, that's what I would have for this. That's why my scale's off, but that's that. And this value and this value are the same by the symmetry of the problem. You guys remember this? So I'm concerned about the maximum shear. Well, the maximum shear occurs here and here, comes right at the dashed lines, which is exactly what. And so we're going to want to do a section at the line to find out what the total shear force is there. So if we do a section at that line, right, so now I'm just looking at, this is the 1/3 point part, right? So I have a force acting here of 20 kilonewtons. What's the shear force on the plate? 20 kilonewtons. So we know that V is 20 kilonewtons. Now presumably, we could have just, by inspection, kind of gotten there. Look at this and say, oh, well, I'm pulling 40 kilonewtons on the top, so that means the top of that bolt is being pulled to the left with 40 kilonewtons. So I got 20 kilonewtons per bolt of shear force. I mean, you should be able to get there fairly quickly. You don't have to do too much, you don't have to do this rigorous an analysis, you know.
So if I was gonna look at that by inspection though, I would assume that somehow the 80 would affect the shear force on the bolts. Why doesn't it?
It does. But what you've got is like you said, as you work your way down, that's what this diagram is supposed to represent.
Are
So,
those?
so in the center, there's no shear in the center of that bolt. Because you've got 40 pulling to the left and you've got half of the 80 pulling to the right. So it's an equilibrium.
So
there's a-
those circles are supposed to be lined up with the dashed lines?
Yeah,
Okay.
that's what I said. I mean, you can kind of see it if you scale this back. Okay. I mean, you remember that from statics? Okay, so the point is, this is what we got. We have a shear force of 20 kilonewtons. So however you get there, there's a couple different ways of looking at it. You can do this, or you can kind of, by inspection, recognize that the bolts have to, the top of the bolts are are holding back that 40 kilonewton force. So there's 20 kilonewtons being pulled back by each of the bolts. So you can do a free body diagram, just that top plate. Oh, well, there must be 20 on each bolt, and that's my shear force. So however you get it, you got a shear force of 20 kilonewtons. Okay. So what am I trying to find?
So then you have tau is the shear force over the area.
What tau is that?
That's the allowed tau.
Right. So, we don't have the allowed tau, we weren't given the allowed tau.
So we do the failure over the factor of safety.
Failure strength tau divided by the factor of safety. Right. So, am I good? Do anything else? Okay,
Solve for A,
solve for A.
solve for
Well, I'm gonna actually do one better and say that's V over pi over 4D squared, because I'm really gonna solve for D. Right. Flip everything around, and I get D is equal to failure stress, or factor of safety times V divided by pi over 4 times the failure stress, the 1/2. And then plug in values. 2.5 times 20,000 divided by pi over 4 divided by 350 times 10 to the 6th, 1/2. And hopefully that gets 0.0135 meters.
How did you know what tau allow is? You didn't?
I use this over here. The allowed is equal to the failure divided by the.
Okay, and how did we find, oh, the failures right up there, good. Got it.
We read. Okay. All right. Did anybody, nobody bother trying to play that? Trust my numbers, it's fine. One of these days, I'm gonna throw something up that's completely wonky. Nobody's gonna know. All right, any questions that make sense? Okay. So, you know how to, so you can design around known load. All right, the bottom one. The tension member is fastened together using 2 bolts, one on each side of the member as shown. Each bolt has a diameter of 0.3 inches. D is 0.3 inches. Determine the maximum load P that can be applied to the member if the allowable shear stress for the bolts is 12 KSI. And the allowable average normal stress on the bolts is 20 KSI. So as is generally the case, materials fail more readily in shear than they do in normal stress. So it's easier to shear a bolt than it is to pull it apart, which should be practical experience should tell you. Right? You ever cut a bolt? How do you cut a bolt? You shear it. Right? So that's going to be the easiest way to
It'd be really fun to try and get it down the center.
okay. You go with that. In the meantime, we'll solve this problem. So, what's the first step?
Free body.
Free body diagram. Oh, no. Okay, now the question is a free body diagram of what?
One bolt.
I'm inclined to think that it might be easier to look at the complementary force, to look at the right-hand piece of the tension member. So I think it might be easier to do the free body diagram on this. Because whatever normal and shear forces are present on this face are the normal and shear forces experienced by the bolt. Okay. Does that make sense? Because that's where the force is applied. So I've got P pulling out here. And what other forces am I going to have?
People.
So not on this member, I have no other P on this member. What other forces?
What's in the middle of the drawing? 60
So,
degrees. and
It's a member that had, actually, it's two members that are joined together,
Right.
and there's a flange on the side of the member coming out towards you that's bolted together. And the flange is at 60 degrees.
Then we have the shear force going,
You see what I'm saying?
Yeah, I think so.
So in other words, normally you would kind of expect, well, if I've got to butt joint these two things together, I'm probably going to have a vertical flange on here, right? So then there'd be a beam with a flat end, and I would bolt that flat end to another beam.
Right.
But in this case, that flange is at 60 degrees.
so we have the shear force along that 60 degree.
So we have a shear force, right? So we have a shear force.
And then the.
What direction will we draw the shear force, up or down? Down and to the left or up and to the right?
Up
Or up.
or down?
Down and to the left. It's probably going to oppose the P,
Okay,
right? Because the member's not, we got to have some of the forces.
and then the normal force perpendicular to,
So we have a normal force and a shear force and a P force. NP and V. Does that make sense? These are the forces acting on this part.
Right.
Right? The forces acting on the bolt would be just the opposite. Right? You'd be pulling the bolt down, right? Pulling the bolt in tension and shearing it in that direction. Okay? It's all good? It's all right? It's all right. Okay. So there's my free body diagram of the right member. Now what do? Stare incessantly at the screen until Dr. Steckenroth enforces us by telling us what to do next. No. What do I do next?
well, no,
It's just, this is the basic same stuff you did in UPhys. I've drawn a free body diagram,
Need some forces.
drawn my forces, I sum the forces.
So we don't know any of the forces.
you can
We
find
don't.
the forces because you know the equations for tau and, or for shear and stress.
Right, so we know the shear and normal stresses, right? And we know the diameter of the thing. We can solve for everything in terms of each other, and then we can come back in, right? So, let's solve for N and V in terms of P. So sum the forces. What coordinate system are we probably going to use? Well, yeah, x, y. What direction is x? What direction is x?
I don't know. If it was me, I'd just put it in P and split N and V the components.
Okay. So I would do it just the opposite.
You would put it in,
N and V are already orthogonal to each other.
right.
So I'm going to choose that as my x and y
Okay.
coordinate
Split
system
P.
and split P.
Okay.
So I don't have to split one thing instead of splitting two.
Okay.
That'll give me one equation for each dimension as opposed to two equations, two unknowns. Okay. So I'm going to define my x and y like that. And then sum the forces in the x direction. All right, so here's my, that's 60 degrees with respect to the horizontal. So this is 60 degrees. And my component of P, this I have a P in the x direction and a P in the y direction. Right? So the forces in the x, that says then that P times the cosine of 60 degrees is equal to V. And some of the forces in the y direction says that P sine of 60 is equal to N. Right? Okay, so now I've got my forces in terms of P, or P in terms of my forces, whichever way you look at it. So I can rewrite that then as P is equal to V over cosine 60 degrees, or P is equal to N normal force over the sine of 60 degrees. So now I have P expressed in terms of both V and N. So now I'm left with the fact that I don't know which of these two is going to fail first. I don't know if this arrangement is going to fail in shear, or is it going to fail in normal load. So I've got to solve each of them and see which one gives me the lower value of P, right? So the P that's going to cause the first failure. I don't have to fail in both directions. I only have to fail in one. So I got to find the P that's going to fail this thing for each mode, shear and normal. And then whichever one's lower is the P that I'm going to use. Does that make sense? Okay. So,
But that will, I mean, in this situation, that would never be the normal,
I don't know.
right?
Let's find out. We're gonna play both in and find out. Okay. So I know that my T allowed, which is V over A, is 12 KSI. So the V then is going to equal 12 KSI times my area, or the P for allowed. P allowed is going to be 12 KSI times the area divided by cosine of 60 degrees. Similarly, the P allowed, if it's a normal failure, will be 20 KSI times area divided by a sine of 60 degrees. So I could actually, at this point, determine which one it's going to fail in, because the area is the same. So I just got to find out whether 12 over cosine 60 or 20 over sine of 60 is bigger. See what I'm saying? And then I can actually go calculate the value. So I don't want to have to go ahead and calculate the value for both of them. I'll just calculate one and find which one's better. So which one, what is 12 over cosine 60? And what is 20 over the sine of 60? 23, give me a 36 big.
23.1.
Okay. So 23.1 is going to be the one that fails first. Right? So that's going to be the smaller one. So now I have to just go back and multiply by the area. So 23.1 KSI times the area, which is pi over 4 times 0.3 squared. And if I trust them, that gives me 3.26 kips. Did you get 3.26, Ben? No, you don't. Nobody knows. All right.
How did you come up with that?
With what?
To get the 3.26 kips. So we
We just plug this, we plug it in here,
Mhm.
and then the area is pi,
Oh, that's the area.
pi over 4d squared. And it's in inches already. KSI in inches is the base unit for stress. Does that make sense to everybody? For what it's worth, the other one ends up 3.39 kips. Just in case you want to make sure it all works out in your head. Okay, so it's pretty close to failing either way.
But the normal force failed first.
What's that?
But the normal force would have failed first.
But the normal force, it would fail in the normal force first in this particular configuration. Now, if I really wanted to make this thing as strong as possible, you know, once I've got this particular configuration, I say, you know, I want to make it hold a little bit more than P. I could adjust my angle so that these two are the same. Find the angle at which the shear and normal failure are both equally likely to occur, and the load that it would hold would be a lot larger. And so the maximum load it's going to be able to hold is at whatever angle corresponds to setting these two numbers equal to each other.
Is that 45 degrees?
No. Just depends on what the shear and the normal failures happen to be for that particular material. So I could do it. I mean, I could solve that right now by taking this divided by this, right? And say that's 1. Yes. Right, because these two are going to be equal. Take this divided by this and set it equal to 1, and then end up with tangent of theta is equal to 1.66666. So whatever the inverse tangent of 1.66666 is, what's the inverse tangent of 5/3? Okay. So 60 degrees is pretty close to optimum. Does that kind of make sense? Okay. How are we doing on time? 7 minutes. Now, we'll try to go back and do one other problem, but see how far we get. I'm going to do that bottom one there, the anchor problem. So let me put this back in here.
So we're doing the bottom one?
didn't get to talk about shear stress last time, we only talked about normal stress. Okay, so this anchor bolt pulled out of the concrete wall. And you look at the surface, the failure surface, and you've got this conical shape and the cylindrical shape. A frustum and a cylinder. Frustum and a cylinder. So along the, and you can kind of see in the diagram, you have a normal failure in the area where you have the cone, it pulled away straight out, and then you had a shear failure in the cylinder region. So, if the shear and normal stresses along these surfaces have the magnitude shown, determine the force P that must have been applied to the bolt. So essentially we have this bolt. And there was some force P applied up here. And essentially we're assuming that there's no adhesion between the bottom plate on that bolt and the concrete that it's sitting in. So we have a force, a V force here, and a normal force here. That make sense? And we know that the stress here is 4.5 megapascal, and the stress here is 3 megapascal. So how do I find P? Sum of the forces. Okay. So what would I sum as my forces?
Well, in the y direction, so we have the, can you assume that the two V's and the two ends are the same?
Yes, you assume symmetry.
So then you have the negative 2V plus P minus, what is that, the 40, then, is that sine 45?
It doesn't matter, right? Sine of 45,
It's the same
cosine
thing,
45,
isn't it?
same thing.
Okay.
Okay, that's almost right. It's probably, well, I mean, depending on how you define V and N, you probably can do it that way. But in reality, this is it's a circular system, right? So if you say it is 2N and 2V, then you're saying this half of the semicircle has one N and this half of the semicircle has one N.
But it's the
It
same.
would probably be easier just to figure the whole thing as one big N.
Gotcha.
Okay? So P minus V minus N times sine 45 degrees. So what's P, or what's V and N? That's equal 0. So how do I solve for N and P? Or N and V? N and V. I need values for N and V, so I can plug in a P. Everybody just stares. 3 o'clock class is just brutal.
Well, V would be tau over, or tau times the area.
Be tau times the area, right. So that's going to be, so P is going to equal tau times the area of the shear. Plus sigma times the area of the normal force times sine 45 degrees. So what's the area of the shear?
2 pi times 25 millimeters. Times 30 millimeters. Is that right?
Very good. Yep.
Okay.
Yep, circumference times the height. Right? What's the area, oops, the area of the normal surface? Caleb's carrying you on today. Somebody else step up there. What's the area for the normal surface? Caleb's smart, you should take the cylinder, that's an easy one. How do you find the area, surface area of a cone? You can memorize it or you can figure it out. If you haven't memorized it, then you're going to have to figure it out. Think of it differentially.
Is it just 1/3 pi r cubed? Is that not
No. You're talking, first of all, that would be volume, R cubed, that would be volume. Think about it differentially. There's going to be a little ring, right? The area of that ring is the circumference times delta H, right? So the circumference times the distance along here, and then we integrate this along this line, and that gives us the total. But we're integrating along a linear function, so it's just the average circumference times the length. You
So
with
just
me?
the circumference in the middle?
So it's the circumference in the middle, which is the average circumference,
Right.
times the length of the frustum, the length of the surface, the length of the cone.
So how do we know what the average circumference is? Because the cone there, it only tells us, it doesn't tell us like.
Yeah, the cone is, it does tell you, look, it's a 45-degree angle. So
Oh, I
it's
see
precise.
that, okay.
So 45-degree angle, so this is 50, and this is 50. So,
I see it.
and it's, okay.
I didn't see the angles on it.
Okay. So the area of that thing is going to be 2 pi times x bar, the average radius there, which is 0.05, times the length, which is the square root of 0.05 squared plus 0.05 squared. And it's the total length of that angle, of that surface. We get the areas, plug that back in, we have values for tau and sigma, plug those in, sine 45, and find P. And just because we're out of time, P is equal to 68.3 kilonewtons. How do we feel? Other than being
Cones are hard.
tired at the end. Cones are hard. Not that many cones.
For the rest of it, it's pretty
It's kind of
straightforward. It's not bad.
So that's the end of the stress section, that's the end of chapter 1. So you should be able to do all the
What does all the
homework.
homework do?
So today's Wednesday, it'll be due on Monday. It's always due, except when we have exams, it is due the class period, after the class period, after we finish. Okay. So there's one class period in between when we finish the material and when it's due.
So So,
But I think actually the homework is due on Wednesday, because we only spend Friday is the only day we're gonna spend on chapter 2. I think chapter 2 is built into the homework as well. Am I right? Yeah, so it'll be due next Wednesday. All right.
and that's all, Josiah?
See you later.
You realize, though, somebody else may take this class someday.